Very good. That will help us because I have about 170 slides in the deck, so this will allow us to move really quickly through some of the groundwork ones. I'm by nature very loud and speak quickly. If you can't understand me because I am not loud enough, wave your hands. If you can't understand me because I'm speaking too quickly, I'm sorry. I did get my PhD here. It took a long time. I'm not to say that I recommend it. It turned out okay in the end. But yeah, that's the one side. Okay, so I've been working in AI and machine learning for a long time. First at IBM and then at Google. And I've worked in a variety of areas, mostly in the kind of consumer side within Google, but in the last few years I've been working in healthcare. And I know that I looked at the syllabus for this course, and it's really an amazing who's who of folks that you've already had who describe a lot of the opportunity here. So there will be, I think that there'll be a lot of familiar messages about what the opportunity looks like, but hopefully I'll give you a slightly different color on it. So the first point is just everybody knows that we already have artificial intelligence in all of our pockets, whether that's consumer products like Photos or Gmail or Translate. It makes things that we're familiar with better, like Google Search, but it also makes entirely new technologies possible, like automated replies to emails and texts. The framework that I use to describe things is there isn't a universally accepted standard as far as I'm concerned, but the way that I parse things out is that artificial intelligence is the endeavor to make machines that have the useful appearance of intelligence. I dabbled with getting an undergrad in philosophy, and I really don't want to get into the meaning of intelligence beyond useful facsimiles thereof. Machine learning is a subdiscipline that's really about making machines that learn from experience. I generally consider that there are some things where we have systems that learn that no one really considers very much artificial intelligence. And the basic point is that we believe now that traditional AI systems were programmed to be clever, and in many cases it's actually better to have them learn to be clever. A few data points in various regions of this Venn diagram, just so that you understand what I'm talking about. IBM Deep Blue was very clearly a great artificial intelligence achievement. It did not involve any learning at all. Contrast that with Alphago, the system that bested world champions at the game of Go rather than the game of chess. That has been entirely learned now, and is also an AI system. But then there are other technologies that we're very familiar with that no one really feels like are AI, like reading handwritten digits on checks has been in automated teller machines since the 90s, and nobody thinks that ATMs are intelligent. I'm also really interested and passionate about the intersections that are coming in with the third field of robotics. Personally, I believe that the combination of machine learning and robotics is going to revolutionize robotics in much the same way that artificial intelligence has been revolutionized by machine learning. The basic point that you're all familiar with is that machine learning is fundamentally a different approach to building tools, where rather than entirely specifying the program yourself, you're actually using data to resolve some aspects of what the program are. So the state of the world that we're in right now is that for many repetitive tasks, it's now actually easier to build a computer system and have it learn to perform a task rather than try to write it with handwritten rules. Just a breakdown of supervised, unsupervised, and reinforcement learning as a reminder for folks that are less familiar. So supervised learning is far and away the dominant technology in all practical applications today. I cannot underscore that enough. And that's learning to imitate correct examples of a procedure. Unsupervised learning, looking for structure or patterns in data, is something that is very interesting. It's very important to data science and exploration, but often it's just about generating hypotheses and understanding data sets that then allow you to build supervised learning systems to accomplish some task. I'm not aware of very many unsupervised systems that actually directly perform a useful function, but they're very important in helping us understand data sets. Reinforcement learning, I do believe, is something that we're going to see more and more of over the next decades, and that's learning by trial and error. It's obviously much less efficient, but it has fewer constraints around it. But all of the work that I'm going to talk about later in the applied healthcare domain is in the supervised learning category. There are some unsupervised examples, but I'll skip those. So let's just, I think I can skip this. You guys are all going to understand this. Yes. Basically, machine learning is fitting the line. But you know, it's amazing when you stand back and you think about how simple the approach in machine learning is for all of these various technologies, is that what we're doing is we have some notion of what framework or family of models that we're trying to fit, and then we're looking for some parameterization of that class of mathematical functions to accomplish some useful task. And it's really painfully simple when you stand back and look at it, that the practical systems, often they take a very specifically defined input, they have a very specifically defined output, and the system that actually renders the classification or regression or other prediction, really the changeable part of it is some parametric expression of what the system is capable of. And supervised learning is always doing something of the form of comparing the system's putative output, its guess, with some ground truth that we have on the side, and then making adjustments to the parameters in order to make a similar error less likely if in fact there was an error. This kind of learning is very simple, but it is actually very general, and relies on throwing a lot of computational power at it, where you iterate through this cycle repeatedly. It's super general though. This really is how we have learned to recognize objects and images. And at Google, we really use supervised learning to learn to do all of these tasks. Whether it's speech recognition, image recognition, or automated responses to email. All of those systems are based on machine learning. One of the big changes that has catalyzed the use of machine learning and artificial intelligence has been the introduction of deep neural networks, or the reintroduction of artificial neural networks, depending on your preferences. And the way that these systems work is by decomposing complicated problems into many steps or layers of pretty simple decision makers. And as an ex-neuroscientist, I can say that this is only the vaguest and most distantly similar model of how decision-making works in the real biological brain, but fundamentally some of the principles do apply and translate, which is that we're going to break computation down into a large number of steps of very simple decision makers, and we're not going to specify what the role is of the individual decision makers in that network. Instead, we're going to let them learn to work together in order to solve, decompose the problem and find a solution. So the way that this played out in computer vision over the last few years has been very, very exciting, where when I was in grad school, most of computer vision was this world where you take an image, you have some handcrafted features, then you have a thin classifier that takes a collection of features and renders some judgment. And there were thousands of papers over here on the left side about generating new representations of data and extracting new features. Indeed, I actually have written some of those. But and a few really good ideas on how to do classification, but progress was kind of slow. And part of the reason for that is that there really are some very hard cases. So if you squint, it's very hard to tell the difference between a muffin and a puppy. I swear that this one in the middle, it's like, I just think it's a puppy, but it's really a muffin. And writing some kind of pixel-based rule for the difference between muffins and puppies is pretty hard, but this is the kind of thing that you can all trivially get a machine learning system to do if you use deep learning. So deep neural networks have kind of fused these two things, where you're both learning, you're simultaneously learning how to abstract the features and how to render judgments. You're not separating cleanly into this notion of we're learning a representation of the data and then we're making decisions about that representation. So this, in some sense, is less pure, but it's turned out to be very efficient, and a lot of the healthcare applications that I'll talk about are really specifically using deep learning. The key benefits here are that it really does learn from pretty raw data and gets you end-to-end predictions. So it's kind of perfect for supervised learning. It's very interesting to look inside these networks and see the kinds of things that they've learned, where they take raw inputs and learn progressively more abstract representations of it in order to be able to make more complicated decisions ultimately. And this was kind of a revolution in the early 2000s, where around from 2010 to 2011. These are performance results on the ImageNet classification challenge, which Fei Li helped to organize, which she spoke here, right? So you're probably all super familiar with ImageNet. Yes. So deep learning really changed the game here in terms of the quality of making these simple classifications. Now, this is not to say that computer vision is solved, because object recognition is only a tiny part of being able to see and understand the world, but we're seeing that these things are changing very, very rapidly, and it's allowing really crazy new things to happen. So this is a little GIF of the Waymo cars, the Google Alphabet self-driving cars that now are capable of things that were really not possible even just a decade ago. It's also allowing us to see in other domains beyond the visual domain. So in many ways, you can use systems like Alphago as learning to recognize patterns and see go boards. And it's been, actually, I really feel that this is amazing work by the DeepMind team in London to be able to make these accomplishments, not just with supervised learning, but then to be able to show that they generalize. So they can actually do it in an entirely reinforcement learning based way. And then here's just a video of one of the labs that we have at Google, where we're using robotic systems to actually generate training data for them to learn grasping tasks. And this is an interesting intersection, as I said at the beginning, between AI and machine learning that I think is going to go really well, and it's amazing how well they're doing. So machine learning isn't magic. It's just a new engineering approach. But it is an approach that has some pretty different properties, and particularly when we apply these techniques to healthcare, it introduces some new challenges. But sometimes people ask, why is this kind of transformation in technology happening now? And it really comes down to my view that to build practical machine learning or AI systems, you need these 4 central ingredients. There's a lot of compute requirements, so you need centralized, high-intensive computing, you need training examples to learn from, you need good tools and algorithms, and you need your own creativity and ingenuity. And until recently, there were really rate-limiting steps on this top row in terms of the availability of compute and the availability of good tools. And the reason why compute is so important is because although this approach is very general, it's really, really slow, and the level of horsepower that's required in order to get these things done is really crazy. So this kind of reminds me of why we were waiting so long to learn to fly, is that there were really decades where people had decent ideas for how a flying machine would work, but they were unable to get off the ground because the engines that they were using to power their flying machines didn't have a sufficient power to mass ratio to be able to get you off the ground. And the first people to fly built engines that were as light and as powerful as possible, and now they've become commodities. And this is very much the same thing that I think has happened with AI and machine learning, where we were kind of waiting for computers to get fast enough, whether those are traditional CPUs, GPUs, or specialized hardware like the Google TPU that we use for some of our models. It's really cool to be able to do things more quickly, but I think that really the thing that makes the difference is that it allows you to engage in the creative cycle. If you can try out an idea quickly and get the results. I just like this picture because I think it's ridiculous that computers are going back to liquid cooling. Yeah, this is just a picture from one of our data centers today. Let's look at that. In terms of tooling, so this is really important. There are a lot of really good tools. PyTorch is great. We use TensorFlow because we helped create it. Then we first released it in 2015. Now it's in version 2.0. It's a really good tool set for open source tool set for doing a lot of AI and machine learning. It's got a lot of it's grown really nicely, but one of the things that we've seen is that as the complexity of the architectures that are available to use in these packages, we actually had to provide more training to go along with it. So we actually have a course now on Google that you can look at and a textbook that goes with it on design principles for building good AI and machine learning systems. And then I'll just talk about some of the places where we're using this in Google. We use it in photo search, we use it in translation, where for the first time it's really gotten levels of performance to be near human levels of machine translation. The nice thing is that you can paste these machine learning systems together and get them to do fun, complicated things. I actually really used this when I was in Moscow a couple years ago, and it worked. Smart Reply is another system that I worked on. It was kind of surprising that this was plausible, that it works, but you can learn what a decent reply is to an email. Smart Compose is something that's, it's really just text completion on steroids, but I'm pretty happy with how well these kinds of systems work, and they use deep recurrent neural network systems in order to be able to make these predictions accurately. But the basic idea is really very simple, is that we're just going to take a statistical approach to trying to understand what the most likely distribution is for a string. And there are many models that you could use to do that, and there are many different parameterizations of similar techniques, but it turns out that deep neural networks are trainable given the data set sizes that are available today. I've also been really interested in how this has changed in terms of not just being able to take things in a domain and classify or recognize them, but actually to build generative systems. So the Deep Dream tools that came out a few years ago are really fun ways where you can dive into deep neural networks and see the kinds of things that they work. And then there's also been a rise in generative adversarial networks. Okay, raise your hand if you've raised general adversarial networks. Okay, smaller group, but still plenty. The idea of a generative adversarial networks is actually really interesting, which is that what you're going to do is you're going to have two neural network systems, and you're going to pit them against each other. So one of them is the generator is trying to generate fakes. It's trying to generate fake images, and then you mix fake images and real images, and you train a separate neural network to try to weed out the fakes. And if the generator gets caught counterfeiting, it should be called counterfeiting. If the counterfeiter gets caught making a fake, it gets a gradient and changes the way that it does things. And this does allow you to produce some really weird things, like you can change the style of a painting, you can change the season in an image, you can change horses to zebras and zebras to horses. It's not perfect, but it's an interesting start. Also, a lot of these techniques allow you to understand a little bit more about what's going on inside these systems. So this was an example that Chris Olah did, where he was exploring, well, what's a canonical example of the barbell class in an image recognition challenge, and it's not just the dumbbell itself, it's usually got some kind of like chicken wing hanging off of it that is representation that it's in someone's arm. But these things are very general, and it just requires these finding domains where all of these things are present. But in order this is a really general and powerful tool set, and there are a lot of different things that you can use it with. And one of the things that we're trying to be cautious about at Google, and we're also encouraging the rest of the community to do, is to be mindful about the ways in which you use AI and machine learning and what the systems you're actually going to build do. So at Google, we've made some very public commitments about the kinds of AI systems that we intend to build and how we can make sure that they're socially beneficial. I'm also on the board of a nonprofit called the Partnership for AI to Benefit Society. And one of the things that we really see is that this is not a simple or obvious process. There are a lot of unintended consequences of building any kind of new technical system, and I think that as technologists, it's important for us to take that responsibility pretty seriously. Okay, so the takeaways for this early part of the talk are the differentiation between AI, ML, and robotics. Google already uses AI and ML in all kinds of product areas. It's not magic, but it is a new tech fundamental. Currently, machines learn best from examples, aka supervised learning. Why is this happening now? Computers might get fast enough, and making it machine learning works requires these four ingredients. And it works in a surprisingly wide array of applications, and that does raise some challenges, but those challenges are things that are better faced together. Okay, so that was the whirlwind introduction before we start talking about the healthcare stuff. Everybody good? Good. Some people are nodding. Excellent. Okay, so with so many possible applications, we really got interested in, what's the area where you could apply artificial intelligence and machine learning where you could have the most impact. Because yes, it's great to find more cute cat videos, but maybe there's something that's a little bit more important. And healthcare seemed like a really obvious answer. But let me spend a little bit of time kind of going through what makes this such an important area to apply AI to. We think that there are about 8 million people per year that die because of lack of quality healthcare. And there are about 100,000 deaths just in US hospitals that are from errors, that are from mistakes. And it seems kind of unconscionable to imagine that we presently have more AI and decision-making assistants allowing us to get directions and text each other than we do in order to get good healthcare. So we are really interested in trying to move the needle on that. But having computers help doctors, this is not a new idea. The idea of computers in the healthcare system have been around for a long time. And if you go to a doctor today, they almost always have a computer. It's not clear that that computer has really helped that much. But what's changed is that in addition to machine learning changing, actually the data availability in healthcare systems has also changed radically. So this is a plot of how many US healthcare systems actually have electronic health records. And even by 2015, we were getting to pretty high saturation levels. And at this point in the US, things are very well digitized. And that unlocks the opportunity that we can actually improve things using technology. So this is an article that I found where people basically arguing that for the first time in history, there's actually enough compute in healthcare to make real AI feasible. So the conjecture is that the same way that computer vision as an individual discipline was revolutionized by the availability of data like ImageNet and compute like GPUs, healthcare is similarly going to be transformed. So now I'm going to talk about some of the actual areas that our teams at Google have worked on in applying AI and machine learning to healthcare in particular. I'll try to highlight as I go some specific principles that we've noticed. Most of the talk will be about the opportunities to apply AI in diagnostics. But then I'll spend somewhat less time on care management and decision support, and then the least amount of time involved on personalized medicine. Okay, so first let's understand machine learning for medical diagnostics. This is the conjecture that machine learning will radically improve computer-aided diagnostics, which is something that's been around for a while, and that therefore drive a massive expansion in their use. So the example that everybody talks about of this kind of transformation is using computer vision to assist folks in reading out X-rays or other radiological reports. My forecast is that this is completely assured from being technically feasible, but real deployment is going to take some time. The same way that it takes a very long time to go from Stanley, a self-driving car here on Stanford's campus, to really being able to buy one in the market, it takes a good amount of time. And some of the reasons for that are that these things are actually appropriately going to be regulated as medical devices. They are, the software that's involved in using machine learning for these approaches has the ability to change doctors' decision making. That's the whole reason why we want to build them, but that means that they do qualify as a medical device. I think it's also important to understand that the explainability and interpretability of these systems is going to be very, very high. When you get a YouTube video recommendation, it's not so important why it was it knew that I would like this particular stupid cat video. But when we're making a determination about somebody's healthcare, explainability and interpretability really have a much higher, it's a really much higher bar. And the other thing that I think is unusual here is that we're usually talking about the effect of a human-machine collaboration. We're not just completely automating an entire process, but instead we understand the endpoints, the effectors, and the inputs are always going to be human-mediated. And that means that we need to build systems that are aware not just of, that we're not optimizing just for some specific metric, but we're optimizing on the overall impact for the system overall. And I'll go through a few examples of areas that we've worked on. We've worked on ophthalmology, we've worked on radiology, and we've worked on pathology, and I will zip through these. So one of the areas that we worked in ophthalmology is diabetic retinopathy, and that's because it's the world's fastest growing cause of preventable blindness. And there's a lot of diabetes in the world, and it seems to be growing. The way to avoid blindness, if you're diabetic, is that you need to get regular eye screenings in order to be able to identify whether your retina is degenerating in this way. And then if it is, there are treatments, they're a pain in the butt, but there are treatments that will allow you to preserve your vision. And this is basically an image recognition task. You're looking for signs of disease on these images of the back of people's retinas. There is a fair bit of inconsistency. So this chart shows each column here is a different ophthalmologist, and each row is an example of an exam of a particular image and case. So if doctors were infallible, you would see that the colors would be completely solid across the board because every doctor had identified this case in the same way. But even in this first row, you see that this particular patient, all of the ophthalmologists thought that there was no diabetic retinopathy, but one of them thought that it was in the middle of the grade. And you see this person here, this is an error, this is potentially a much more serious error. This is a case of somebody where if they happen to get that ophthalmologist, they would have said, oh, your diabetic retinopathy is mild, when in fact there are a number of people who say that it's very severe and require immediate treatment. And this is not particular to ophthalmologists. It's not particular to fundus imagery in general. Any place that you look in medicine, there is tremendous inter-clinician variability. And that's because the tasks are so hard and there's so much uncertainty. So the idea is to try to help doctors and make these things look more like rainbows. See rainbows. All right. The way that we did this was actually pretty simple, which is that we start with retinal images. We apply the same kind of object recognition system that we use at Google for other things. We did label a fair number of a very large data set. So we had 130,000 images of eyes, and we had 54 ophthalmologists label them. We ended up with 30,000 images. And you can build, using supervised learning, a system that is better both than ophthalmologists and now is at the same level as a retinal specialist. So this means that you basically built this system that is on a par with the best people. One of the concerns, though, is that people are like, well, wait, aren't neural networks a black box? And the answer is no, not really. So, for example, this is a case of somebody who has moderate diabetic retinopathy, and you can use techniques like salient maps or integrated gradients to be able to identify which parts of the image most affected the decision. So these little green spots are the pixels in the image that if you change them, would have the biggest impact on the system's confidence that, that this person had diabetic retinopathy, and that lets you know that they were informative areas of the image. And the nice thing is that we're actually putting this in practice now, so we're actively screening folks using this technology in collaboration with nonprofits in India and Thailand, and doing real clinical trials to complete this loop and say, okay, well, it's not just about the area under the curve, which is all very nice, but let's actually see it work for real patients. One of the things that's really interesting here, though, is that you want to approach this as science, and there really are new discoveries to be made. So we were really surprised in the retina that we discovered that there were new things, even just in that domain. So, for example, you can regress out someone's chronological age just from an image of their retina. We could guess their stated biological sex at a pretty high rate. But you also have to be really careful about confounds. So this is another example where someone showed that you could predict stated biological sex by looking at an MRI of the head. But further investigation shows that, well, actually the accuracy is mostly driven by things that are outside of the brain. So if you're thinking that there was a difference in the brain regions that was allowing you to identify this, that's not it at all. It's that there's morphological differences in the head. So it's very easy to, particularly if you have a foregone conclusion in your mind, to follow that. But even within retina, we see a whole bunch of things that you can predict that we were very surprised by, ranging from whether or not you're a smoker to your systolic blood pressure. And this is really interesting because the idea of being able to extract cardiovascular risk factors from a retinal image is potentially pretty useful. But it's not just about that one modality. We've also done things in 3D retinal imaging. This is some work that was done by the DeepMind team in London, where we're actually using segmentation models to be able to represent to identify different tissue types within the retina itself. And again, we've been able to show that this has allowed us to make diagnoses as well or better than trained specialists. So that's it for ophthalmology. I'll touch on some of the work in radiology. So we've got a bunch of projects in this area. I'll just talk about one of them, which is lung cancer screening. So lung cancer is a disease where it's very clear that if you catch it earlier, your chances of survival are much better. So the blue and the red curves there are survival rates for stage 1 lung cancer versus stage 4 lung cancer. And so you want to catch this early. And it turns out that we've shown that you can use deep learning, actually using 3D convolutional neural networks to go through the entire volume to identify specific materials. Because the way that this works is that you put someone in a CT scanner and you actually get a 3D image, but the images are a little grainy and it's a little hard to interpret. The approach that we took here is one where it's not just stick something into a convolutional neural network, it's actually a multiple tiered model. There's one model that's actually trying to identify regions in the lung that require further attention, and then we point a separate high-res model at those regions, as well as a low-res model that gives kind of global context. Put those things together, and you can have multiple approaches to be able to, you can ensemble multiple approaches to really get better accuracy. And this is a curve here. The red, green, and yellow points are real board-certified radiologists trying to identify whether there will be cancer in this patient within 2 years. And the blue line is the performance of these systems, which is quite good. One of the things that's interesting is that it's not just about catching false negatives. It's also about false positives. So this is an example of a false positive where the humans said, oh, well, that is suspicious. That person should get a biopsy. But it turns out that our system correctly recognized that was just a scar on the lung, and it was not going to, the biopsy was actually negative. So the way that, and this is another area where you really want to drill in a little bit, and we again used some integrated gradients to be able to see that the attention was not just on the nodule itself, but to the surrounding area. And so the theory is that the way that it works is that in positive cases, so this was a positive case, the attention is very focused on the lesion itself, but in the negative case, there's something about the surrounding image that indicates that it may be something about the vasculature that actually lets you know that this is not well vascularized and therefore is much less likely to be a malignant tumor. It's not collecting blood because it's not growing. I'll talk a little bit about how we apply this in another domain, which is pathology. It's a different kind of problem. I should say the reason why I'm doing multiple examples here is to highlight that it actually requires creativity. So the leftmost one looked a lot like an ImageNet challenge and was super simple. The middle one, we had to have these multiple scale models in order to be able to actually localize regions. In pathology, it's different again. So now this is an example where, okay, there's a lump, whether you see it on a CT or you feel it, and then what you actually do is you get the biopsy, and that biopsy, that slice of tissue, goes to a lab. That person looks at it under a microscope and determines what kind of cancer treatment you need. And there are also errors in making that, and that's because it's really, really hard. These images are gigantic, and about a quarter of sentinel lymph node biopsies, which are the biopsies that help you tell whether or not you've got localized cancer or really bad metastatic cancer, and about a quarter of them, the grade changes if you get a second opinion. So that means that there are a lot of cases where there are false positives and false negatives. So this is an example of a study that was published in JAMA. This is a confusion matrix, and everybody that's on the off diagonal is someone whose diagnosis changed when it was shown to other specialists. Now, of course, the further off the closer you are to the diagonal, the less severe an error it is, the less likely it is to have an impact on your treatment. But the point is, we want to get these things down, right? We want to get everybody on the diagonal because every one of those is somebody's mom or cousin. In terms of the machine learning, this was an example we're actually working with the regular doctors. It was really important. We discovered that we observed that as pathologists are making these determinations, they zoom in and out and change objectives and look at different scales. And so we built a machine learning model that actually looked at multiple scales simultaneously and fed each of those into their own independent machine learning models, deep networks, and then you ended up with a system that actually could tell the difference between cancerous and non-cancerous tissue in sentinel lymph nodes, and was also robust to the kinds of things that you might be faked out. So I would not, as someone who's not a pathologist, but has looked through microscopes, I might think that that thing on the left was a tumor because those cells look weird. But in fact, that's a tumor mimic, and a trained pathologist knows the subtle differences between just weird-looking cells and something that's actually a tumor. We're able to show that with these systems, because the task is so hard, human attention really limits total performance. So a pathologist with unlimited time looking at a slide only has a 0.73 ROC, which is a quality metric, and our system is up over 0.9. But there are real-world considerations here that are very, very important and you cannot ignore. So we saw that small changes in image focus, some of which would only annoy a pathologist, our machine learning system was actually quite sensitive to. So we actually had to first build a system that identifies images that are out of focus and discards them. And to get this into real clinical practice, you don't just end with the model, you have to find some way to work it into the actual workflows that doctors are going through. So we built this system where you can add an attachment on an existing microscope and be able to overlay machine learning predictions in real time. And that's actually the real latency for it to be like, oh, that looks bad. We won't watch the video. Okay. So that was the whole diagnostic section. Now we're going to go quickly through care management and decision support. Okay, so care management and decision support is different than this pure diagnostic setting. So the idea is that if machine learning can assist in everyday decision making, like route planning, we think that it should be involved in healthcare as well to improve quality, lower costs, and catch errors. So the idea is that right now, the electronic medical record that your doctors use is really dumb. It's just kind of a data entry system, largely used for billing and documentation, both of which, documentation at least, is very important. I do think that this is going to happen. I think everyone in the industry thinks that it's going to happen, but it's going to take a long time. And part of the reason for this is that currently there's a lot of data, but data portability is low and inconsistency is high. There are tremendous problems here with disentangling correlation versus causation. There are not a lot of experiments that you can do in this space to detangle them that are ethical. And it's pretty difficult to figure out. It takes a lot of time and effort to figure out what really actually helps in real clinical practice. But it's so important that we feel that we have to try. So 1 in 4 patients will have an adverse event in their hospitalization. Many of these are just mistakes that happen and are then corrected. But we would like to alert folks as early as possible. And again, in working with these doctors, it's because the tasks that doctors are given are not humanly feasible to be done completely correctly. But some of the things that we believe are that prediction is a cornerstone of prevention. And so having machine learning systems that are better predictors of what is likely to happen next is very important. The clinical attention is really, really important. And right now, too much clinician attention is given to documentation as opposed to the really hard part about attending to the patient and making the decision. And we know for a fact that most EHR data, most of the things that go into that electronic medical record are never used. They are never looked at. A lot of it is never used for any real clinical purpose. So we published a paper a few years ago showing that you could actually take data from electronic medical records and use it to make some interesting predictions. But it's really pretty difficult because the real world is super messy. This is actually a real schema for the data representation that is used in some of these systems, and the schema are always changing. So building a machine learning system that operates on them is really hard. And most of the work is really data science work. Fortunately, things are getting better, so there are some new open standards that are helping with interoperability. So we use the FHIR standard, Fast Healthcare Interoperability Resources. And it's an open source standard that we're extending, and it's been very helpful. And the way that we make these predictions is that we take electronic medical records and we unroll them as time series. So each of these little gray boxes is an event on a timeline of a patient's hospitalization. Each one of those little resources has a whole bunch of data inside it. We want to build machine learning systems that can look at that timeline and make real predictions. And one of the things that's hard, though, is that the information that's in each of those nodes is itself incomplete and ambiguous. So, for example, there might be a clinical note that contains saying that this patient was given LEVO. Well, what is LEVO? It could mean these are all synonyms in real medical records for this same notion, which is it's actually medication. But the good news is that places like Google have already helped us solve some of these problems using text understanding techniques. And there are some surprising cases of things that you can search for. So we've used things like text embeddings, which are high-dimensional representations of semantic concepts, and demonstrated that we can use them for regular semantic quantities for learning the relationship between cities and countries and their capitals. And indeed, when we look at medical records data, you can learn the same kind of associations to identify which medications go with which diagnoses. And then that allowed us to build systems that were able to make pretty interesting predictions where standard state-of-the-art clinical models, this is, real doctors obviously potentially do considerably better than this, but clinical models that were in the state-of-the-art are there in white, and if you apply deep learning and throw data at the problem, you can really pick up those scores quite a bit. The thing that's really interesting here is that these systems, not only do they make predictions more accurate, but they also make them earlier. So the point that was reported in the numbers is the prediction at the moment that someone is admitted to the hospital, which is just the difference between, at that middlemost point between the baseline system and the deep learning system. But the thing that's interesting is that even if you look 24 hours earlier, the deep learning system is still above the quality that the regular system, the traditional logistic regression system, had at the time of admission. And being able to decide things sooner in medicine, we think makes a huge difference. And so we really think there's a giant potential impact to move towards anticipatory care. So the idea is, you think you're moving along in the green dots, and then some bad thing happens in your medical event, and that causes you to fall off your original care plan. Nurses have to make changes. But if what we could do is we could recognize earlier that something was going to happen, then we could put you on a more appropriate care path sooner and actually get better outcomes. And one of the areas that we focused on, this is something we did in England, was acute kidney injury, which is a particular a problem in a hospital where people's kidneys get in distress, and the sooner you catch it, the better the outcomes are. And we actually worked with real clinicians to evaluate the impact on outcomes at the University College of London, and we looked at patient outcomes, hospital metrics, and a whole bunch of other things, and we were able to see that this had a real impact in terms of the mean time to treatment, and then the overall cost savings to the hospital, because when you catch cases sooner, they're considerably less complicated. I'll skip this one. I'll just say that medical imaging isn't always diagnostic. Sometimes it's actually about planning and decision making, and we've also applied this successfully to deal with, to assist in radiotherapy guidance, where you have to segment out organs, and I'll skip that one. Something else that's interesting is a lot of health is actually dictated by environmental factors. You can use machine learning in some interesting ways to try to understand and forecast things in the environment, sort of machine learning powered epidemiology. I think that this is an area where we're going to see a lot of growth. And then I'll just zip through the last area, which is personalized medicine. The conjecture there is that machine learning is going to unlock our ability to leverage more information about the individual to guide personalized care. So for example, using omics, whether it's genomics or proteomics, to inform prescribed medications. Right now, this is only used for very expensive, very rare cancer drugs, but I think that it's going to happen more broadly. This is still sci-fi at the moment, but I think it's worth investigating. The kinds of areas that we've been investing in Google are in trying to promote those tools. So we actually have an open source project in genome variant calling, which is one of the early stages in terms of identifying what the individual genotype is. And we built a system that uses deep learning to go from raw sequencer output to identify the individual genetic variants in the person, and have demonstrated that the system works very well compared to previous state-of-the-art systems, and even does so on entirely new data sets, so data sets that it's never seen before, and that's something that's really, really exciting. I'm going to skip the protein stuff and just go to the kind of takeaways is that you really have to appreciate that clinical care is super complicated and messy, and so your nice clean machine learning solution may not work in real situations. And there are real issues of fairness and representativeness that need to be dealt with when you apply machine learning in healthcare cases. Our belief is that safety and fairness are things that you can take a technical approach to, and we've got a bunch of papers around on this, particularly in the healthcare domain. And I'll skip some of these. But the real point here to me is that it's a new technology. It's just math. It's magic. But you have to find ways of applying it in an interesting way. It does make new things feasible in healthcare in particular, and I think that there's really potential here to improve the health of a lot of people, and that's why I'm excited about it. Okay, that's the end. So, Yeah.
How difficult is it to approve an algorithm in the FDA?
Yeah, so one of the big differences, so the FDA has actually taken a really good and constructive approach to software as a medical device, particularly in using machine learning techniques. And their early draft guidance on how they're going to approach this is pretty encouraging. It depends a lot on whether there's an existing device that does the same task. So if there's an existing device that already does this, and you're just trying to do it better, it's much easier. It's called a 510K clearance. But if it's an entirely new indication, and there isn't an existing device that already does this task so-so, it's considerably more difficult to get an approval. It's a years-long process, and so it's very much not for the painters. But I think that it's appropriate that these things are regulated really carefully. Yeah.
You mentioned about the rule-based deep rule looking at the previous AI system, and we know that revolution of deep learning started from 2012. So we know that there are many expert rules in the medical field. So Google, how do you merge the traditional based AI and the deep learning?
Yeah. So so I think real engineered systems usually have layers of rules, fuzzily applied machine learning determinations, and then human judgment. In most real-world systems, whether it's something that's, whether you're launching a space mission or making popcorn, there's some set of interaction between rules and human decisions. And I think that if you approach things as a complete system, it's very useful. There are contexts in which rules are extraordinarily helpful, particularly in terms of they're much more transparent. It's easier to make them fair and equitable. And in some cases, they're still the most appropriate thing. But one of the things that's been really interesting is that it's clear that, to me, that doctors are not covertly applying a set of rules. Yes, they have some rules, and in cases are simple or clear, they'll go back to them. But a big part of the role that rules are playing in human judgment is it helps you learn, but that eventually, when you're really great at something, you're often recognizing patterns, which machines now do very well, or you're reasoning out arguments, which machines still do quite poorly. And so I think it's really about finding a balance where you stitch these things together in an intelligent way. I don't think rules are going away. I think that it's just that trying to use rule-based systems for really hard tasks turned out to not work as so well. Yeah.
I was curious as to why you put decision support in the same category as care management, whereas I thought it would probably be closer to like computer-aided diagnosis.
Yeah. So the interesting thing about, so part of the view that I have is that diagnostics, when I think about diagnostics, it's a case where you really cleanly know what the input and the output is going to be, and they're pretty circumscribed, right? So it's like an image or a blood test or a single observation, whereas clinical decision support and care management is more like navigation and planning problems than it is like classification and image recognition. I agree that it's kind of there's a spectrum in some sense, but at the one extreme you just have classification and localization, and at the other end you have planning. A lot of computer-aided diagnosis is more like classification, and clinical decision support is more like planning and routing. Yeah?
Yeah, I just was wondering your thoughts just on just like the getting the data set and just like what you're thinking in the future, it would be possible for like smaller companies to do well, or like if becoming access to the most data is necessarily the most important. Like
Yeah. So I think right now our healthcare system does not learn very well from its own mistakes, and doctors do this very deliberately and manually, particularly in in some of the specialties or in acute care where they actually review cases that have gone wrong and learn collectively. But I think that technology presents an opportunity for us to learn really broadly. And my view is that the appropriate way to deal with this is to find privacy-preserving and secure ways for the healthcare system as an ecosystem altogether to learn from historical data. And to me, it will go much better if there are more parties who have appropriately privacy-preserving, anonymity-preserving opportunities to make contributions. And that's some of the reasons why I think these open source standards like FHIR are very interesting. So there's this notion of smart apps on FHIR as this little movement where the idea is that, well, okay, we'll try to build machine learning systems where give small companies an opportunity to build tools that can interface with a larger healthcare system to solve some small problem. Because I don't think that this is something that's, it doesn't make sense to limit it.